So in this problem we will see some plotting exercise. So first what is given to us is a DC signal of 5 volts, and how will it look like when we plot it? So DC signal is basically nothing but a straight line. So this is time. The DC signal is just a step function with magnitude 5 volts. So this is a signal that is given to us. So assuming that the circuit is switched on at some particular time t equal to 0, then you have u of t to be the DC signal. Okay. Otherwise, if the DC signal is said to be on forever, then you have a straight line which just extends from minus infinity to plus infinity. So either you can represent this as a step function or just a constant which is going from minus infinity to plus infinity. So let us say that this is a DC signal which exists from minus infinity to plus infinity. So then this is what we represent the DC signal with. Now this is the plot of the signal that is given to us. Now if it is passed through a rectifier, now we have two kinds of rectifier, the half wave rectifier and the full wave rectifier. Right. So the half wave rectifier just gives us whatever is the positive value of the signal. The full wave rectifier will in some sense take the modulus or absolute value of the signal. So full wave rectifier is something which gives us the absolute value of the signal, and half wave rectifier is something which will give us only the positive value of the signal. For a DC signal, here it is given to be plus 5 volts, right? So plus 5 volts, which means the output of the rectifier, irrespective of it being a half wave rectifier or a full wave rectifier, will exactly be the same thing. So DC signal given through a rectifier is the same. The input and output are same. So there is no difference. The rectifier does not do any kind of alteration to this. Okay. Now what if we have a signal which is an AC signal, which is basically a sinusoid, okay, and its peak amplitude is given to be 2 volts and the frequency is given to be 50 hertz, which means you have a sinusoid, something which goes on like this. The peak value is 2 volts and the frequency is given to be 50 hertz. So if the regular frequency or the linear frequency is given to be 50 hertz, then what is the angular frequency? Remember, 2 pi times 50 will be your angular frequency. So what is your period here? Now the period is 1 by 50. So the period here is 1 by 50 seconds. Now if you feed this to a half wave rectifier, what would be the output? Now the output would just be the positive values of the signal, and so on. Now the output of the full wave rectifier would be the absolute value. So the output would be something like this. So the peak value is still 2. Peak value is still 2. One thing that you can note here is the output of the half wave rectifier is still periodic with the same frequency 50 hertz. But the output of the full wave rectifier is periodic. This is also periodic, but the frequency has now increased. Now this is 100 hertz because the time period earlier was this entire duration, but now the time period has reduced by half. So the time period has reduced by half, which means the frequency will double, and that's what has happened here. So half wave rectifier does not change the periodicity, but full wave rectifier changes the periodicity. Okay, now what if you add this DC and AC together and then pass through the rectifier? What do you think will happen? So if we add this DC signal, then we will get something which looks like this. Now what is the peak value? And the peak value turns out to be 7 volts, and what is the least value that it takes? The least value that it takes will be now 3 volts. So now this is an entirely positive valued signal, which means when you pass it through the rectifiers, you will get the same signal. So the full wave rectifier or the half wave rectifier will produce the same output. And is this periodic? Yes, this is periodic. And what is the period? Now the period is 50 Hertz. So now we started out with the DC signal that did not get affected by the rectifier at all. Then we had an AC signal which gets affected, and the periods could change depending upon what kind of rectifier it was. And then we had the sum of DC and AC signals, and as you can see here, this does not get affected by the rectifier at all. So individually, if you see these two signals, they were affected differently by the systems. Okay, let's take another example. So here, this is also a plotting exercise. What is given to us here is the signal cos 2 pi t. Cos 2 pi t has a frequency of 1 Hertz, an angular frequency of 2 pi radians per second, and you are just simply multiplying that with another sinusoid. So we have cos 2 pi t you are adding 1 to it, which means it's just a DC shift. So let's say A is, let's start with 1. So 1 plus cos 2 pi t would have been just, so this is 1 plus cos 2 pi t. So what's the maximum value it can take? The maximum value it can take is 2, and what's the minimum value it can take? It is 1 minus 1, which is 0. So this is cos So this is cos 2 pi t plus 1. Now what are we doing? We are going to multiply this with cos 200 pi t, which means we are multiplying this with something which has a frequency 100 times larger than this. So it should look something like this. So you multiply these two signals. What would you get? So you would get something like, so this is what you get. So this is what we call in communication as amplitude modulation. So you take a sinusoid of very high frequency and then change its amplitude depending on whatever is the message signal. So in this case, the message signal is cos 2 pi t. So here the message signal always needs to have a frequency which is very, very small compared to the sinusoid that you are going to use for modulation. This is what is called as amplitude modulation. So clearly, as you can see, what happens, the envelope here of the high frequency signal gets modulated. It goes up and down based on whatever is this particular, the low frequency signal. So now the low frequency signal is completely positive. So you get an amplitude modulation, something like this. So what happens if A is minus 1? Okay, what happens if A is 0? That is easier. So if A is 0, then all we have here is 1 cos 200 pi t, which is basically nothing but this high frequency signal directly. So A is 0 is straightforward, you are not changing the amplitude of the high frequency signal with anything. What happens if A is minus 1? What do you think would be the case? So if A is minus 1, then 1 minus A cos 2 pi t minus 1, this is the case. So what would be the maximum amplitude here? The maximum amplitude here would be now 0, and the minimum amplitude would be now minus 2. In other words, this entire signal gets flipped. So This is 0 and this is minus 2. So this is what we have as 1 minus cos 2 pi t. Now, if you multiply this signal with our high frequency signal, what would we get? We will get so this is what we would get when you multiply 1 minus cos 2 pi t with a high frequency signal. As you can clearly see, whenever the first signal has high amplitude, the second one has low amplitude and vice versa. So, whenever this multiplies 2 with the high frequency signal, this signal multiplies 0 with the high frequency signal. So, whenever the high is obtained here in this signal, you will get the low here in the other signal. So, they are out of phase with one another. There is a phase shift, and this phase shift is with respect to the low frequency signal. So, this is what we call as the amplitude modulation, and as you can see, the value of A here determines what is the phase with which we transmit. So, the A here is an important factor, and typically it is kept to be less than 1. It is somewhere between 0 and 1. Okay. Now we have another kind of signal. This signal is often used in wired communication. Let's say you have an USB cable and then you connect the USB cable between your phone and your laptop, or you have an HDMI cable that you connect between your monitor and your laptop. There is some kind of signals that is going inside this wire that carries the bits ones and zeros, right? Typically what is used is what is called as a non-return to zero signal. So you have waveforms that look like this. So basically whenever there is a 1, then you have a rectangular pulse which goes from minus 1 to plus 1. Now this would represent a 1, a digital 1, that is a bit 1, and the 0 is represented by a signal which goes from plus 1 to minus 1. So this is represented by, so this represents the bit 0. Bit 1 is represented by a pulse which goes from minus 1 to plus 1, and bit 0 is represented by a pulse which goes from plus 1 to minus 1. So this is called non-return to 0 because the pulse never goes to 0. The pulse is always going somewhere between plus 1 and minus 1. So hence the term non-return to 0. With this encoding scheme, can we represent the bit sequence 1 0 0 1 1? Now let us say we start at time t is equal to 0 and we have 4 time slots. Okay. Each time slot represents 1 bit. So to represent the bit 1, we know that the signal has to go from minus 1 to 1. So the first time slot signal will look like this. Okay. This represents 1. Then it is 0. So for 0 it has to go from plus 1 to minus 1. So we have the next time slot to look like this. And the third time slot, the bit is 1, which means it remains here. And for the fourth time slot, the bit is once again 1, so it will remain at plus 1. Okay. So we have 1 0 1. So this is the non-return to 0 signal representation of the bit sequence 1 0 1 1. So we can use our rectangular pulse to generate this sequence. So we can represent the signal completely using the rectangular pulse. So how do you represent that? So now we have the first pulse, you can say the rect of t minus some t naught, and the third pulse once again can be represented using rect of t minus some t1, and the fourth one is rect of t minus some t2. So how do you get this rectangular signal at each point? So you can take the regular standard rectangular function and then do time shifting and scaling. So you need to do time scaling, because if this length is greater than 1, you will have to do time scaling. If it is exactly equal to 1, then you can just do time shifting. Okay. So this gives us a rectangular signal based representation for the non-return to 0 signal. So you can sum all of these things and then multiply them with 2 and subtract 1. So if you do this, then we get exactly the non-return to 0 representation using the rectangular pulses. So this is what we call as a non-return to 0. There is another representation called the return to 0 representation. So we will see what is that. So in the return to 0 representation, bit sequence 1 is represented by something which starts at 0 and ends with 0. In other words, this is our pulse. So this is bit 1, okay, and bit 0 is represented by something very similar, which starts at 0 but goes in the negative direction and comes back to 0. This is bit 0. So this is a return to 0. It starts at 0 and comes back to 0 again. So this is what is called as a return to 0. So once again we can represent this also using rectangular pulses. So bit 1 would be some rectangular of t minus some t naught, and bit 0 would be minus of some rectangular of t minus some t1. Okay. So in the same way, whatever we did earlier, we can also represent this return to 0 signals also with rectangular pulses. Let us see how the representation looks like for the given sequence 1011. For 1011, the return to 0 representation will be something like this. This is bit 1, started at 0, went to 1 and came back to 0. Okay. And then we have bit 0, start at 0, go to negative value, come back to 0. This is bit 0. And then once again we have bit 1, another bit 1. So this is bit 1, this is bit 0, bit 1, bit 0. So this is the return to 0 and non-return to 0 representations. These are actually used in wired communication signals. So if you cut open your, let's say, a USB cable and connect it to an oscilloscope, you will see something like this. You will see rectangular pulses, something like this, and you can, in fact, from the oscilloscope you can know what bit is being transmitted at what time if you can zoom in enough and then see what is the rectangular pulse.